Brian, thank you. And you got banger in also by speaking precisely at the moment when the bell sounded, you bossed it, which is another English phrase which I can, those of you who are familiar with the tradition, our speakers are in discourses encouraged to go until exactly an hour after they started, which I think the last 5 minutes is the longest 5 minutes of your life.
That's right.
Yeah, you did really well.
Worried about the stick.
So look, we have people in the room. We have people online as well. You're all welcome. We have Alana, who has insights into what the people online are thinking. I'm going to start with a couple of words from her. Folks, we're going to do about 15 minutes of questions, and then those of us here are going to go and have a drink with Brian in the library. I think the temperature there is less than 35 degrees, but those that you have thermometers can bring them with them, and we can check it when we get there. So keep your questions brief. Ideally have them as questions, if you will, and the mics will come to you. Alana, what's online thinking?
Well, so unfortunately, I can only see questions within this multiverse. But we've had people logging on from Bremerton, America, Kingston, England, Athens in Greece, so all over the world are tuned in with us this evening. The first kind of observation we've had, and a question to build from it, is the globe of the universe, with the Milky Way going around the equator, is a very kind of anthropomorphic view of it. How, and I'm going to build on that, how do we break away from ourselves when we're looking at all of these huge questions where we're not in the middle of it? Where do you kind of start with that?
Right. Well, most people, when they hear that I'm a cosmologist, say, oh, that explains your phenomenal hairstyle. And I'm just joking. They either do that or they ask me for their horoscope when they find out I'm an astronomer. But actually, those two things are related. Cosmos and cosmology. And cosmetology, cosmos means beauty or face. The universe presents a face to us. And we see that, and it is beautiful. And the more you know about it, the more beautiful it gets. In fact, the Milky Way is actually sort of a redundant phrase, because Milky Way galaxy means Milky Way, according to my sons at least. And we do personify things. I should point out that not all cultures perceive the same things we do. In fact, the Inca astronomers were quite exquisite observers of the night sky. When they look at the night sky from Chile, where we build the Simons Observatory, they look not at the bright constellations, Virgo, Gemini, Aries. They don't care about the bright stars. They look at the dark, dusty globules. They have their own constellation names, and some of them are doozies. There's one called the toad. Okay, fine. There's one called the llama, but my favorite is the umbilical cord of the llama. Imagine you go to a bar as an Inca 1,400 years ago, and you say, what's your sign? I'm an umbilicus. I'm an umbilicus. So all cultures do that. They have different origin stories. Science is attempting to make precise an origin story. But as Richard Feynman said, science is the belief in the ignorance of experts, not the wisdom, not the knowledge of experts, meaning that what I say tonight could be completely wrong, as Faraday warned. And some of you out there or in here can prove us wrong or come up with a better, more refined idea of it. And that's the goal of science. Science is never settled. Science is an infinite game. And yes, we're human beings that play it. And so it's natural to make it appear as similar to things that we have familiarity with as the Incas did with the things they saw around them.
Thank you, Brian. And if you have questions, then, by the way, it's good that the answers to questions are getting applause as well as the talk itself. If you have questions, do give us a wave. Can I build on, okay, good. We're going to go here, and then later we're going to go there. While the microphone's going, quick question on Karl Popper's terms, right? So you talked a little bit about the difference between maths and physics, and Popper says you really are going to be trying to disprove stuff. But new theories are really cool, right, and coming up with them, they're beautiful. Is it really the case that you're trying as hard as you can to disprove the really cool stuff that you're coming up with? Because experiments to disprove things are what you're supposed to be doing, right? Yeah,
so it is true that it's I won't say it's easy. I'll get into a lot of trouble for my theorist friends. Some of my best friends are theorists. But to predict a theory, oftentimes it's said that a theorist needs to be right once in her career to have a phenomenal career. An experimentalist can be wrong once and his career is over, meaning that you can produce a supply that might exceed demand, and there might be more than data can predict. It's familiar from things like string theory, for example. It may not even be testable. The predictions are so vague and all-encompassing. It's like what Popper originally was concerned with was astrology. So he used to say that people would say, as an astrologer, you go out tomorrow and it'll be a lucky day for you. Well, what does that mean? It's not precise. To be precise means you rule something out, not that you accept something as being true.
Okay, thank you. Yes.
Yeah, so you have this idea of the inflationary multiverse and then the idea of the many worlds interpretation of the multiverse in that respect. Does it make sense to ask, like, what space are these universes expanding into? Is that even a sensible question to ask? And is the many worlds multiverse sort of reconcilable with the inflationary multiverse?
Okay, so what space are these things expanding into?
Right.
Good question.
So the balloon or this beach ball kind of misportrays what's happening. You could almost see this beach ball expanding or something like that. That is not what we believe. What is more similar, what would be a better depiction, would be to put little dots on this trampoline here and then distort it by putting the cannonball on it. The dots would move away in the space itself. They wouldn't expand into the third dimension. They would stay affixed to the second dimension of the sheet. So too with our universe. Our universe has galaxies and stars embedded within it. The stars aren't moving, the galaxies are, all receding away from each other, but they're expanding in the same space itself. So it's not as if it's expanding into another space around it, although we don't know for sure. As I said, there could be literally another Big Bang that happened approximately the same time ago as our Big Bang, in a region of this vast four-dimensional infinite space that we would then come into contact with, and we would have a microwave background which would bear the imprint of that microwave background, and where they are touching, the intersection of two spheres in 3 dimensions results in a one-dimensional or circular pattern. So there are predictions made by colleagues, some of whom are in the UK and Canada and elsewhere, that you should look for these patterns of circles in the sky that would be indicative of a collision of multiversal bubbles. So in that sense, yes, they could be in a vaster space surrounding us, but we don't want to think about it expanding into this room, but more stretching along the constant contours that exist in presently.
Thank you. I think the microphone's there, yes.
If we have the electromagnetic field and you can generate an electromagnetic pulse, then with the scalar field, is it possible to generate a scalar pulse?
That's a very good question. So actually, I didn't describe how the universe results in a gravitational wave background due to the fluctuations of the scalar field, which is what the question is asking. So in inflation, the scalar field has a value, just like the thermometers do at each point in this room. But then they start to change. And you can visualize that as the value of the field evolving in what's called a potential. And the scalar potential here is the height above the floor. So this ball will move faster as it traverses, trading its potential energy, which is a scalar, for kinetic energy, which is another scalar, but it will acquire a velocity, which is a vector. If this was a quantum ball, the ball, if you zoomed in on it, wouldn't roll smoothly towards the bottom. It would jitter back and forth. And those quantum fluctuations would cause this region of space to expand slightly faster than this region of space, and that would then have perturbations in the density of space-time itself and its curvature. Into those potential wells, matter would agglomerate, dark matter first, then ordinary matter, and then you would get this pattern here. But you'd also get a reverberation of the sheet itself. And that's the analog of a gravitational wave. So it's a very prescient question. You would observe that. You would observe the fluctuations of the scalar field, effectively generating curvature perturbations and so-called gravitational wave or tensor perturbations. Very good question.
We have good questions at the Royal Institution. We've got some online, and then I think we're going to probably the hottest spot in the theatre, which is right up at the top there. Alana, what else is going on?
So just building on that scalar field discussion, we've got a question from Les. And Les has asked, so if scalar fields are thought to have started inflation, what was the trigger point, if there was one, to stop that inflation?
Okay, so another phenomenal question. So when I did this demonstration with the supercritical fluid, there was sort of a symmetry that would occur, that would get broken in certain spots. But if this petri dish were infinite in size, it would keep going. It would keep spawning these little fractal remnants that have the shards that would appear as if their own island universes. So what happens with inflation, and that terminates the inflationary process, is the universe is expanding as the potential, as the scalar field rolls down from what's called a false vacuum, it evolves slowly rolling, picks up speed, and as it's picking up speed, imagine the sheet is expanding also, and it could be expanding faster than the speed of light. As this sheet expands, eventually there's energy that will be dissipated between the ball rolling and the sheet, almost like a friction term. That friction is the Hubble expansion itself. That would cause eventually what's called reheating. That would then cause the universe to begin with a bath of unimaginable, hellish temperature, even hotter than here. And that would then provide the energy necessary to spawn particle-antiparticle pairs and spawn the matter content of our universe.
Thank you. While I mop up Faraday's original plate, we'll take a question up there.
Yeah, so again, just building on that idea of the scalar field, you talked about how the gravitational waves are produced. Is that indicative of gravitons, or is it all quantum particles?
Yeah.
And also...
Well, hang on. We'll take one at a time because we're almost out of time. I think the gentleman mentioned graviton.
Yeah.
What's a graviton?
So a graviton is one of my top 3 favorite particles. There's a proton, the graviton, the crouton. I love... so a graviton is the quantum analog of a gravitational wave, the same way a photon is the quantum mechanical instantiation of a electromagnetic wave. So we call it that, but unlike a photon, we don't know that gravitons exist because we don't know if gravity is a quantum theory or a purely classical theory.
Good answer. There was a question, I think, let's go that way.
Firstly, thank you for the brilliant lecture. It's really enjoyable. When you talked about the cyclical cosmology theory and the idea of sort of recombining into another Big Bang and how that could also combine with the multiverse theory, I was wondering if the universe is constantly expanding at a faster and faster rate, and the only evidence of the Big Bang came from billions of years ago, what's to say that another Big Bang couldn't be happening now within our own universe, and it's actually a sort of concentric spherical model?
So there are limits on how spherical and how far apart the nearest Big Bang, as you say, might be from us. And those limits are exceeding the characteristic horizon size of our current universe. So we don't believe the universe has curvature on scales shorter than the observable universe's diameter, which is quite enormous, and in fact 3 times the age of the universe multiplied by the speed of light, because the universe is also expanded. The question of whether or not you could have a cyclical universe and you could have an initiation of another universe via the acceleration that we call dark energy. It's not clear if dark energy is Einstein's brilliant blunder. It's not clear if it's what's called a cosmological constant. It could be a variable constant, if that makes sense. It could be something that appears on human timescales or even galactic timescales to be constant, but is slowly evolving, that its energy will decay and be lost and converted to some other form of energy, namely photons. And that actually does occur in Sir Roger Penrose's model of cyclic conformal cosmology at the end of an aeon, and in the bouncing cosmological model of Paul Steinhardt, Anna Aegis, and Neil Turok. So it is under active pursuit.
Very sadly, Brian, we're kind of out of time, so there's a few things we need to do. Firstly, lives of Brian. There are a lot of Brians in the universe. Some of the American people who do this stuff are called Brian. One of our own Brians, Brian Cox, has narrated a virtual reality guide to the universe. We're going to be trying it out in this theatre. As you mentioned, a lot of innovations were first demonstrated here, including moving pictures and colour photography. Here, it's not the first time that you'll experience virtual reality, but it is a time that you can experience it. So look online if you'd like to sit in this theatre and have a virtual reality exploration of the universe narrated by our Brian, then you can do that. Now, as you've noticed, this thing has not just been about our lecturer, but also about our demo team and our heritage team. We have Charlotte, we have Mike, who's mostly been working on the ventilation this evening, Isla and Dan. I don't know if they can come out, they probably can't, but if you can give them a round of applause wherever they are. Secondly, the advantage of being in the building, and we're particularly grateful to members and patrons that have chosen to join us as part of this continuation of our nearly 200-year tradition. We'll continue the discussion in the library, and there is a bar there. Those of you at home, sort out your own drinks. But we'll be there, so please join the speaker in having that continuation of the conversation there. Look, this is a talk about the universe. Many of the principles of the universe were discovered here. On the way out, look at the carpet, and you will see the patterns which Faraday discovered of the field lines around a magnet are recapitulated in the carpet that you'll be walking on, so look at that as you go. But also a lot of the instruments and experiments that Faraday originated are here. This is a living museum, the Royal Institution. The items that you see in front of you and that you see in the cases downstairs were built in order to explain the principles that Faraday and others in this building elucidated about the universe. And I was delighted to note that as Brian was putting together the experiments with the demo team, in many cases the modern instruments and the modern elements didn't work as well as Faraday's. And we got, literally telling the truth, we brought out Faraday's from this store and they worked better than the current ones. It's very rare to get a talk that covers the entire universe, but also explains so eloquently what the Royal Institution is about. I'd like to thank all of you for coming and being part of this, but please join me in thanking our discourse speaker, Brian Keating.